Okay, let's start. So, so when I was grading the average rate animator and the generalized piecewise, so those were from a couple weeks ago. So I noticed something that the timing of those assignments was to apply what we were learning in class at the time, but that didn't happen with everyone's project. So I want to talk about that. So we were to, for the average rate animator, it was to graph this secant line given a starting point n and then a change in x of h. So the coordinates of this point were determined by n. So what are if this is the function f, then what are the coordinates of that point? N and f of n. Okay, and so we've got a point on that line, and then based on a change of x of h, we could get the rate of change of that line, right? How would we get the rate of change of that line? We would have this point here, right? What are the coordinates of that point there? And from that, we could get the rate of change, right? So we could write the rate of change as all over, which just ends up being h, right? So yeah, n plus h minus n, totally fine, but just ends up being h. So look, we have this point, and then we have this rate of change. So, but there was a handful of you, or I don't know how many, but some of you still wanted to use mx plus b, right? So mx plus b would be this value right here is b, and what relevance does that have here? Not really much, right? So it's the y-intercept of the secant line, but relative to the graph and what that secant line would be for, that y-intercept wouldn't really have a great relevance. And so rather than figuring that out and then doing mx plus b, we could just apply that y final was y initial, right? Plus change in y. This was the product of developing that linear formula we worked on for a week or so pretty hard. Is dx and then dy, and then y final is y initial plus dy. So what is y initial? F of n. And dy we can get by m times, and what's dx? Okay, no, actually, so no, hold on a sec. So when we're writing this, this is for an arbitrary point on the line, sorry. So we're expressing every point. We're not expressing this point anymore. We'd use that for the rate. So now we're expressing, this is our x final, y final. So it can be an arbitrary point and can represent every point on the line. So really we need to start again here. So yes, f initial is f of n, and then so then we have the rate, which we got there, times. So it'd be x minus what? N, right? And then this m would simply just be that expression right there. So do you see how if you apply this principle, there's no back calculating a y-intercept, which is kind of irrelevant anyway, right? So we just trying to practice applying this. And now that we're getting into you're writing these piecewise functions, again, let me reiterate for those who are still working on the assignment now due Thursday, okay, this is going to be much more effective, efficient, and relevant rather than y equals mx plus b. And hopefully we're realizing that as we do these these projects. And if you're not, then let's have a conversation, okay? So then come get help. But this is really about, we're seeing this thing over and over and over again. And And mx plus b isn't really the helpful tool that that we need. Okay, and so this same I could redo this same kind of argument looking at a piecewise function, right? Because when you get to a piece in the middle, what do you have? You have a starting point and you have a rate of change. You do the same thing. Okay. So if you got a C or a C minus, one of the reasons people didn't get the C plus was that you were using mx plus b, and that was one of the reasons. If it wasn't a C plus. Okay, questions about that? Yes, please. Okay. Why? Why do you have to do that? If you're teaching lines to the idea of rate of change, constant rate of change, then that's we can have that form and we can make sense of it and we can make sense of B in certain situations, but it doesn't have to be the centerpiece of it the way it is in the traditional curriculum. So I don't really know what the Common Core standards. So you guys have a class about Common Core? Some of you. Yeah, so that would be a good question. I would guess that the Common Core is a lot more in line with our treatment of it than just MXPB. But yes, when you get into a school, you're going to have certain structure of what you're teaching, and so you have to balance that, right? You have to figure out. I want my students to have something that's relevant and meaningful. I also have a job to do according to the district, the school, the department that I'm in. So you have to figure out what the right balance is. Yeah, it's going to really depend on the school that you end up in. And so then when you're interviewing for schools, you want to really find out what their philosophy is. And that's going to be, that's going to be important for you when you're interviewing for jobs. Okay? Other questions? It's a great question, though. Okay, so then you have this written assignment, and so okay, so I think this is the same problem that I gave to you. Is this the same problem that I gave to you? Is that exactly the same? You were to do A, right? You were to find the A function, is that right? And the numbers and the situation, the setup are the same? Okay, and here we are again. We got our piecewise function. We want to use the starting value from the previous interval plus the rate times dx to generate this function one piece at a time. And so then prior to this, did we actually manually find the accumulation at the approximate accumulated height at 5 seconds? Did we do that? I think we did that. Did we do this? And so what did we do? So this is really key. So for where we're going, this is so that assignment is important. Developing that A function one piece at a time is very important to get the feel of what that accumulation function is like. And we're going to test it in a second, make sure you had it right. But where we're going, what do we say? We want to write that A function with one rule instead of a bunch of rules, right? Because it's going to be a lot more efficient when we have more intervals, right? If we had 20 intervals, that would mean 20 lines in our piecewise function. 50 50 intervals, 50 lines, etc. So when we write the one rule, we're going to go back to kind of thinking of it this way, looking at what would be the accumulated height for like a particular value, and what was our strategy for that? What was our strategy for finding accumulated height for a particular value of time? Can you say what our strategy was? Brianna. What was our overall strategy for getting this accumulated height at 5 seconds, a particular time? Okay, so completed intervals is an object, it's not a quantity. So what? Okay, adding up the change in height of the completed intervals, is that all? And adding the change in height within the current interval, right? And when we did that, I think we got, what did we get? Oops. 14.28? We did that maybe last Tuesday or Thursday, I don't remember. We got 14.28 meters. So your function that you developed should give you the same value for A of 5, right? So if you were to take 5 seconds and put it into your function, finding A of 5, you ought to get the same thing, 14.28. So I want us to take a few moments to do that, right? So just to see that, what is the function doing when you want a particular value of that function A? Well, it's doing this, right? It's going to, in essence, add up all the height from the completed intervals, changes in height from the completed intervals, plus the change in height from the current interval. So everyone take your own homework, and you're going to work through what would this function do if you plugged 5 into it? How would this function that you came up with compute the value of the dependent variable when the independent is 5? So that may take a little time to walk that through. Okay? So you're going to do that with what you came up with, and in the end, we're hoping that if you get 14.28, good chance your function is right. Okay? Does the task make sense? So if you want to use GC for calculations along the way, that's fine. But we kind of want to learn how does your function work, right? What are the guts of your function to actually spit out a value? Okay, and if you didn't do it, you partially did it, or you know it's wrong, then you can use mine, okay? But if you think yours is right, don't look at the screen, use yours, okay? Use yours to check it. But if you know it's wrong or you didn't finish it, then you're going to use mine, okay? So it's going to take a little time, okay? I understand that. I want you to do it so you understand how that A function works, right? just make sure it's right. It's the same. It's the same. It's just that. Yeah, it's the same. But the point is that we created a function RT so that we could build AT. So that's the idea. So from an approximate rate function, we can build our approximate accumulation function. So we're using it. We're just using it. But yes, you're correct. If you just have R0, it ends up being the same. Did it work? Did someone get it?
But you don't got even that bad because it takes us like 29 actual.
The idea was you to walk through the calculations of how the function is doing it.
What did you do?
Yeah, that was yes. Okay, so this is what we want to avoid. That's why I said to use functions. Use functions. You can avoid this getting off. You mean like this one? Yeah. So by the time you get to 8, 9, and 10, this is 9 again. So this is really awful, right? Like it's so long. If you actually define 10 different functions, you can avoid that. You're not using functions. You're just using equations. You're just grabbing equations. If you actually define a function for each one of those segments, you can avoid this telescoping something to do. It'll avoid this thing of having to keep adding another term. So by the time you get not just one, it's hard to read.
So it's one of the functions, just those terms.
No function for each line segment. Instead of just wrapping the equation, actually define a function for each segment. We're back to the same principle again. Same principle. Without functions, you can't use it. Without functions, you can't use it. Okay, is it working? You guys work? Okay, so we'll just like another minute, and if you still haven't gotten after a minute, hopefully you just got the idea of it, and you can finish it later.
Oh, I had a question.
Okay, so just take another minute to see if you can finish or make more progress. Okay. Yeah, that would be that line right there. Because yeah, 5 is between 4.5 and 5.4. So you gotta start there. Well, that's your function. Your function says the rate is speed of 4.5. Now you're applying that function at 8 and 5. You're not gonna change it. Your function's right. There's no x there. Okay, so on your project that's due Thursday, you want to avoid that, the way you did it, and have it like this, right? And this is a lot more efficient. Just, maybe you did do that on the project. Yeah, okay. So we'll talk about that in a second. not a piecewise function. So that's why I said do 10 different functions. But if you actually define functions, then you can have this kind of setup rather than right. That's what I said, 10 functions. 10 functions. Yeah, because when you get to 8, 9, and 10, they have these. That's yeah. So that was the instructions. I said 10 functions. Use 10 functions. Y equals something with x is just an equation. It's just graphing an equation.
So instead of y function
Okay, so if you didn't finish, hopefully you got the idea of what your function is doing to calculate a value, right? This recursive thing. So let me talk about the project that I extended to Thursday. So in the setup of the framing of that project, I told you for the a function to define functions, you guys. So writing y equals something with x's is not a function. That's just a formula. It's graphing just an equation. Okay. So what truly a function? You want to define a function. If you define a function for every piece, 10 functions, then we can have a lot more efficient. So it won't be piecewise like this, but this will be the feel then of your file, rather than these equations that just get longer and uglier and worse, right? Each one adding another term than the previous. So we can avoid that by using functions. And so that's what I want you to do. So there's a difference between an equation and a function, okay? And that's why I specified using functions, so that you have this potential to make a lot more efficient kind of presentation of how the math behind graphing that accumulation function. Does that make sense? So not piecewise, but instead of piecewise, you use 10 separate functions, one function for each piece of the piecewise thing, and then you can avoid this telescoping sum for each subsequent line segment. Yes, Billy. Sorry, Kendall. Oh, so for this very reason, because if they were on the left side, then I couldn't pull a of 0.9 because it would be in this interval. Yeah, so we need all that this is all the completed say accumulation from all previous intervals. So that has to be defined in the previous interval. There. And if it's defined on this side, it just won't be able to do it because it'll refer to this line, which doesn't have anything to do with these. Yeah, so you'd be an infinite loop, but then also it wouldn't have anything to do with these. The accumulation of the previous. That's what we want. Does that answer? Okay. So did what I say about functions and it makes sense. So then I hope that's a step in your journey of appreciating functions, right? Like what they can do for you. Okay, that just in this case, a simple equation cannot. Last chance. Questions on the oil slick part 2 due Thursday. Okay, so if you're not sure, so people are asking, I got lots of emails asking for help. People are coming to the office. It's awesome. Okay, that's great. Please keep getting the support you need. I want to be available and approachable. So, but then there's also a little bit on you to come get the help you need. Okay, come ask. Okay, so back to this. So in trying to take this accumulation function and take it from a piecewise to a one rule formula, this is going to be the idea behind it. This is going to be the idea behind it. Right? So let's summing up what? Summing up all the accumulation from completed intervals plus the little more accumulation in the current interval. Okay, so what we're working on right now can be summarized in this statement right here. This statement. You know how fast the quantity's value is changing at every moment. You want to know how much quantity you have at every moment. So how would we know how fast the quantity's value is changing at every moment? What would we have that we would know that? What's that? Is it constant? Yeah, rate of change function. It could be changing, right? It could be a changing rate of change. We want to know how much of it we have at every moment. What's that? What's our goal? To build an accumulation function, and we want to do that, like I said, with a one rule function. Okay. So here is a generic kind of situation. We worked on this last time, right? We practiced with this terminology here. So A is the starting value where we want to start accumulating. The red graph is our exact rate function, so that's we know how fast the quantity's value is changing. And then the black horizontal lines is our approximate rate function that we get from the exact rate. And then we know we have the completed intervals and the current interval. Okay, so if we wanted to know how much we had at x equals 6.75, this would be the general idea of that, right? How many completed intervals do we have? Can you see? The intervals are, the red dots are marking off the intervals, or the partition is the red dots. So how many completed intervals do we have? 3. Okay? Then the fourth interval is the current interval. So calculating how the amount of net accumulation at 6.75 would mean summing up the accumulation from the 3 completed intervals, and then the change from the current interval. So this is kind of a generic situation that we're going to use. We're going to set forth on this journey of trying to write the accumulation function in one rule, and this is how we need to think about it. That this is going to be the sum of the changes from completed intervals plus the change from the current interval. Okay, so then I have some questions for you to think about. So I'm going to guide you, but let you do as much of the work as possible. Let you. So I have some questions that are going to be some important questions for. We're working on this, so you can just work in groups. Extra? All right, so I'll go back and put the illustration on the boards. It's a little bit easier to see on the screen, but let's just go through those questions. The first question will be, so first of all, if you look down at the bottom of the page, we're numbering the completed intervals, j equals 1, 2, and 3. See that? The numbering of the intervals, j equals 1, 2, and 3. So the first question is, and let's just talk through the questions, and I'm going to let you loose, and everyone can work their own pace. What are the x values needed to express the rates, right? So that's the open parentheses, right? What x values are needed to express the rates? And those are going to be representations using the symbols that we have in the picture. Second, then we want to express the x value for the rate of the jth completed interval. So we want to generalize that. So you're going to figure out the ones individually, and then we're going to come up with a formula for the x value for the rate in the jth interval, okay? Then we want the x value for the rate of the current interval. So now moving over to the last one. And then we have some, then we're going to imagine that the current value of x is not in the fourth interval, but the 101st. So how would you express A of 6.75, how would you adjust or make a variation on what you see up here to express that the current interval is the 101st? And then the last question, let's just go with FR. So let's hold off on the last question for now, okay? See how we do on these first 4 questions. And I'll put the illustration, it's a little easier to see on the screen. I'll put that back up on the screen. So there you go. So just the first 4 questions, and you can work together on this. Okay? So I left them blank, so you can fill them in. If you want to fill in those X values, you can fill them in.
So instead of writing these out, condensing them into self-sufficient functions,
Okay, is that a void? Is that a void? These sums that get longer and longer.
You're just saying.
Okay.
Oh.
Starting, the X value is starting.
What X value do you want? Oh, it's not gonna be what X value.
Okay, so the current, the current interval has nothing to do with the J's. So the J's are only for the completed intervals. Don't use anything to do with J. Okay? But you still can use everything else. A, delta X, whatever. But J is just reserved for the numbers of the completed intervals. Does that make sense?
You're not just gonna put delta X with one, right? No, A plus one delta X. Yeah. What are the X supposed to be right? I think another way to word it is what are your independent, if they're part of the rate, you do that. Yeah. Because that's the current one, right? Are we doing a generic current one?
The same way that you did the completed. Yeah, it's the same type of thing that you did for the completed. Does that answer it? You're talking about the X value for the rate.
Yeah, so the second question is basically saying what would you input into the rate function?
Yeah, but there's only one, so it's not gonna involve J. So J is just for the completed intervals. So there's just one. You just got one X value for the rate. That's it. So it doesn't involve J. It would still work if you called that the 4th interval, but we're not doing that. It's not the 4th interval. It's the current interval. So yeah, if it were the 4th interval, then the formula would still work. Is that what you're saying? But it's not the 4th interval. It's the current interval. No, because we don't want J to be associated with the current interval. So you have it. You already got it. That's it.
That's it?
Yeah.
With a 3 on it?
Sure. For this situation, you're doing it for this situation.
Oh, that's okay.
Yeah.
So you just don't use it.
delta.
So we just do.
the rate. Get the rate. Just the x value to get the rate, you guys. That's the you gotta focus on. This is the x value to get the rate for that interval.
Yes, oh, yes, 3.
The x value to get the rate. You might not have room for the last that fourth question there. It might not be enough room, so you might do it on the back or in the notes. I wasn't thinking about the answer. No, you don't. You shouldn't, right? No.
How does that have to do with express A of 6.75? Oh. Yeah. Oh, that's the 101st answer. Yeah, I don't know how to. It seems like 2 separate questions. Is it like express in terms of A of 6.75? Why does it say express that? That has
Yeah.
nothing to do with the 101st interval.
What's that?
That has nothing to do with the 101st.
No, so instead of there being 3 completed intervals and then the current interval, suppose that it's the same A to x, but it's 100 completed intervals in a current interval. How would you express A of 6.75?
So instead of splitting this into 3 intervals, it's now just 2 intervals.
Right. 100 smaller intervals, so that the current interval is the 101st.
Okay, so there's 100 of these.
That's right.
And this is still 6. Yeah, the last one we're multiplying that. We just want the dx is just different, but we still call it dx. The dx is just teeny weeny because we're doing it 100 times, so it's teeny weeny. Well, delta x is really big. Dx is always dx is a little bit, but we're still writing it as delta x. So this looks the same. Right? For the last one? The last one? Yeah. It still looks the same because it's the same thing. But delta x is just now smaller, but we don't really care what delta x is because then it's just say delta x. Yeah.
So you could just write this same thing again?
Well, we would need a bunch.
Okay. That's the key.
But I don't want to write them.
Okay, that's all. How do you express that? Again, this is like another product.
It's plus 100 and I'm writing something like that. I'm not sure if that's what it is. Yeah.
Oh, so yeah, so are you finished or are you still going?
Yeah.
Yeah. Where'd that come from? What's that? Okay. Sorry. Sorry.
She's cheating.
Yeah?
Is that? I know that's just recursive.
You got the right idea, but you kind of got some things flipped here. So, what is n? So,
And this is which jth completed interval, right?
well, that's what j is. So it's like you introduce this new thing called
so
n.
j
when really,
is the interval
that's
number.
J.
Oh, okay.
Okay.
Got it.
Yeah.
Okay. This is what I have so far. And we're debating.
What are you debating about?
Well, Sing and Peter are debating that this should be 100
Okay.
and not 101.
Okay.
But the thing is, it should be 101 because it's j minus 1, so it counts the 100th interval. Because the 100th interval is completed, right? And now we're
But the
currently
last completed interval would have, what would your value of j be for the last completed interval?
It'd be 99. Base or R of 90, R of 99. R of A plus 99.
So this was 3 intervals, right?
Right. And that's 2.
And so then your last x value was 2 delta x, j minus 1. So if you have 100 completed intervals, then your last x value should be 99.
99.
So it should be 100 or 101? 100. You see? Okay, I walked around and lots of you had, either got it or something really close, so let's work through it together. So I want to write A of 6.75 if instead of what? Instead of 3 completed intervals, how many completed intervals do we have? So if the 101st is the current interval is the 101st interval, that means we have 100 completed intervals, okay? And so that would mean I would have what? Instead of 3 things added together here, 3 of these, 100 of those added together, okay? So obviously we don't want to write those out. So we need something to represent adding 100 of those together, which a lot of you utilize appropriately, which is what? So who thinks they got it? Genevieve. Okay. I'm going to do something here to help clarify what we're looking at. Okay, what was it again?
A plus parentheses j minus 1 and parentheses dx.
Okay. Dx or delta x?
Oh, delta x.
Okay.
Parentheses to end the right thing times delta x. Plus. So that's the sum part.
So what is it that you've told me so far? What is that?
100 completed intervals.
Okay, those are an object. That's an object. 100 completed intervals is an object.
The accumulation of 100?
Right. It's the sum of the changes from the 100 completed intervals. Okay. And then?
And then plus rate of a plus 100 delta x times dx.
Okay, so I just wrote down what she told me. I wasn't writing it down because it was necessarily right or not. So others of you agree? Or do we need to talk about it? Ron? Okay. Right. 101 here. He wants to change.
Okay, so technically it's 101 minus 1 still, right?
So Ron is asking, should it be 101 or 100? Here's how to ask a question to answer so you can think about this. How many intervals do you have to traverse across to get to the left side of the current interval? That's what we're saying. How many intervals do you have to traverse across to get to the left side of the current interval? Ron, is it 100 or 101? Does that make sense? So really what we're asking is, how many intervals do we go across to get to the left side of the current interval? Are you changing? Okay, so now he's saying 100. Does that make sense? That's what we're saying. What was that? Okay, so then this one is, should this be 1 to 100 or 1 to 101? Should that be 100 or 101? Ben, so why do you think it's 100? Okay. So for the first interval, we go across 0 intervals. That's why it's j minus 1. So for the 100th interval, we have crossed how many? Jose's got it now. In the 100th interval, we've crossed across how many full delta x intervals? 99, right? 99 to get to the left side of the 100th interval, and that's what the j minus 1 is for. Okay, other contentions with this? So far, Genevieve's version is holding up. Anyone challenges? Okay, so we're not far from getting this, right? So we're kind of close. This is going to be the feel of this one rule version of A. Pretty cool, huh? So now the question is, it's not that we're gonna, when we come to a situation, we're gonna know A, and we're gonna know X, and it's not that we're gonna know how many intervals. What are we gonna know? We're gonna know delta X, right? So the things that we would know would be A and X and delta X, not A and X and the number of intervals, right? So delta X would be a given, whereas the completed intervals would be more the determining or the determined thing. So that goes to the last question. Let's look at the last question. If A equals 2.1 and X equals 6.75 and delta X is 0.038, express A of 6.75. Now that's kind of a leap. So what question really, what intermediate question do we want to ask first before jumping right to expressing A of 6.75 for this last? So what intermediate question do we need to answer first? How many completed intervals? So this is, we need this, right? So we need how many completed intervals. So I'm going to show you a file. This is the next thing that the next assignment. And what's cool about this is I'm going to use it as a didactic object to help you develop the math that you're going to need to build it. Okay? Right? So we're still learning the mathematics behind it, okay? And to learn that mathematics, we're using this as a didactic object. And then once you learn that mathematics, then you'll have the tools to build it. Because the mathematics that I'm teaching with it is the mathematics you need to build it. Okay? So here's a simpler example. If A is 2.1 and delta X is 0.83, and let's just put and say X is, so this is X here. The value of N is the current value of X. I can change that up here. Okay, so the value of N is the current value of X, 11.75. So we got to figure out how many completed intervals we have between 2.1 and 11.75 if delta X is 0.83. Do it however you can. Do it however you can. How many completed intervals are there starting at A to X? There we go. Maybe that's better. Do it however you can. How many completed intervals are there between A and X? If A is 2.1, X is 11.75, and delta X is 0.83. No, this is a new example. If you do the example on the paper, it's kind of a mess. So we'll start with an easier example. So this is a different example than the paper. Did anybody just count?
Yeah.
Yeah, totally valid. How many are you just count, right? How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 completed intervals. Okay, but we need math, right? We need math to do this for us. Too small. There we go. Let's make it a little bit worse. 2, 3, 4, 8. There we go. You can still count that. Okay. So you might be able to count, but it's discouraged. How many completed intervals are there between A and the current current value of x, 11.75. Now if delta x is 0.218, 0.218. Okay, everyone's going to figure this out. Okay, everyone figure it out for themselves. It's okay. I love the enthusiasm, but we just want to hold it back so everyone gets a chance to think about it. We got to figure out how many completed intervals we have in this situation. Okay, let's see.
Last one's about 0.26.
You guys get it? Okay. Okay, how about Jordan? Did you get it? Can you share how you went about this, counting the number of completed intervals? Can you explain it? Jordan, yeah. And so can you maybe give a little like reasoning? Why is that doing what you want it to do? Otherwise it's just a formula, right? So did you come up with that yourself? And what was your thinking to come up with that? Josh, what do you think? What? Okay, can you explain what are the quantities involved here? Why is this formula calculating what we want it to calculate? Can you articulate that at all? Morgan. Okay, so it's the total change in x, right? The total, right? Good. How many chunks of delta x fit into this whole length, x minus a? Okay. And when you did that, what'd you get? 26, okay? All right. And so, number of completed intervals is 44, right? Okay, and so some of you know there is a mathematical operation that does what we need. What if that turned out to be 44.9? Then how many complete intervals would there be? Still 44, okay? So some of you know there's a mathematical operation that does this thing. It would take 44.9 and return 44. It would take 44.26 and return 44. But if you got to 45, anything 45 point anything, then it would return 45, right? So it's returning the whole value part of the number that you got. And that's what we want. We don't want rounding, right? We don't want rounding here. We want the number of completed intervals to be the whole number part. And that is what operation? So this is the floor. Okay, so the floor does this very thing. It takes 44.26. It doesn't round down. It just chops off the 0.26. So it gives the greatest integer or whole number lower than the one you have. It gives the greatest whole number that's lower than the one you have. Well, unless you have a whole number, right? So then it would just return that whole number. So to get that, it's this symbols here. It's like you do like big brackets without the tops. So in GC, all you do is type floor, F-L-O-R, and that pops up. And so what do we have? What was our example? 11.75 minus 2.1. That's the total width of the interval, right? And we want to divide that by the width of each interval, 0.218. And so it gives us 44. All right, so this is what gives us our number of completed intervals from A to X. Let me show you the file just so for those who, and get it on the video, for those who want to get going on this next assignment. Okay, so all this stuff that we've developed in class today is going to be crucially important for not this next assignment, but the next one. Because the next one you're actually going to be, we're going to be graphing. I'll show you that too. But make sure you're taking good notes in class, retaining it, saving that. Okay. So here's this file. You can choose any value of A that you want. So I'll come up here, 1.7. Any value of delta X, 0.43. And then I can animate it. What does it do? It shows, it's really fast. It's better. Okay, so what is it? It does several things here. It generates the approximate rate function. Okay, so the current value of X is shown increasing through the delta X intervals. And it generates the constant rate function. And so notice that this technique of using this A from, remember we did A as a member of 1 to 10? This isn't going to work anymore because we could have a lot more than 10 intervals. Okay, we could have a lot more than 10 intervals. So we can't use that technique anymore. We're going to have to use some of this new stuff that we're learning to accomplish this. Yeah, I'm happy to. It's just some cosine variation. Yeah, it's just a wavy, non-symmetric function based on sine and quadratic. But if you change that, if you change g, I can change g, and it will work for the new function g. So I can come in here and just say do 1/2 x cubed. It's going to be too steep. All you got to do is change it, and it works for the new one. Okay, so if you want to get started on this one, otherwise Wednesday night I'll send out the email to respond to for the current one. Okay. Keep the questions coming, you guys. If you need help, make sure you ask. Okay.